Hey everyone, welcome back. So first things first, we are closing in on 100,000 subscribers on this channel. Right now that number is 99,692, and by the time you watch this video, it'll be higher. And if I'm quite honest, I don't know exactly how to feel about that just yet, which is why this is not a video talking about all of that and how I feel about that. We'll have a separate video on that after we actually cross the mark, and after I've gotten my thoughts and feelings in order about that whole situation. But rest assured right now, one thing I do want to say for sure is a big thank you to all of you for commenting, for subscribing, for liking videos, for supporting in every possible way that you have been doing. It means a whole lot to me. Again, we'll have a separate video on that. This video is talking about distances in data science. So we've had some previous videos talking about some distances, but not others. We've used distance measures in many of our videos, but we've never had a dedicated video on here are all the ways that you have available in data science to measure the distance between two vectors. And so briefly, we'll go into all the different ways you have to measure distance and the pros and cons between them. But before we get there, let's talk about why it's even important to measure the distance between two things in data science at all. I would argue that any data science problem, whether you're talking about natural language processing, time series analysis, or anything else, at its heart, at its core, requires some notion of knowing which of your entities are similar to each other and which of your entities are different from each other. So those entities can be different things. In an NLP problem, they might be words. In a time series problem, they might be seasons or points in time. So no matter what your entities are though, part of your problem is likely going to involve knowing which entities are similar and which entities are different from each other. So then you can either treat those in different ways so that you can cluster them together so you can figure out how the outcome variable is correlated to things that are similar or different for all sorts of reasons. So because distances are so important and so core to data science problems, I think it's going to be very important to understand all the different options and the pros and cons you have for each option you might choose. So with that said, let's kick things off by talking about the most widely used distance measure in all of data science, the Euclidean distance. Just to show how widely this used is, if you ask someone to measure the distance between point A and point B, well, they're probably just going to draw a straight line between these two and say the distance is whatever the length of that line is. And that is so commonly understood as the notion of distance that we don't even tack on the word Euclidean in front of that. It's just called distance for the everyday person. And even for most data scientists, it's just distance usually. It's kind of like the all-purpose flower of distances in the data science world, where no matter what problem you're working on now or in the future, if you need some distance measure and you kind of don't know which one to use, you're probably going to be safe by just using Euclidean distance. It's pretty much a safe bet. As we'll see, not always. There's some use cases where Euclidean distance is absolutely not the right thing to do. But in most cases, it will work. If we plot all of the points that have a Euclidean distance of 1 from the origin, which is that red dot, you get this perfect circle. And that makes sense, right? Because if the Euclidean distance is the straight line distance between the origin and any point, and we're saying, what are all the points that have a straight line distance of 1? Well, you're going to trace out exactly that circle of radius 1. The reason I flash this visual on the screen is because when you frame the problem in this way, of what is the Euclidean distance of some point from the origin specifically, that gets a special name, which is called the L2 norm. So the L2 norm is just the Euclidean distance of something from the origin. Now we just talked about all the pros of the Euclidean distance, easy to understand, useful in a wide variety of problems, intuitive, but that doesn't mean it's without its cons. Two of the biggest cons of Euclidean distance, and this applies to some other distance measures as well. The first is that the items in your vectors need to be normalized, need to be on the same scale for any of this distance measure to make any sense. To illustrate that point, let's say you have just a two-dimensional vector. The first feature in that vector, let's say, is measured in feet. The next feature in that vector, let's say, is measured in inches. Now, if you take two such two-dimensional vectors and you just blindly take a Euclidean distance between them, you're implicitly saying that a 1 foot difference in your first feature is equivalent to a 1 inch difference in your second feature, and that's probably not what you want. So that's why it's very important to normalize or put all of your features on the same scale, either by doing a min-max normalization or a z-score normalization, whatever you want to do. But something like that is necessary for these distances to make any sense. The other con of Euclidean distance is the curse of dimensionality, We have a whole video on that linked in the description below. But this basically says that as the number of dimensions in your vector grows, let's say it's 100 or 1,000 or 10,000, taking the Euclidean distance between two such vectors does not really make any sense anymore. Euclidean distance in higher dimensional spaces doesn't really give you the outcome or doesn't really make sense. And so that's something to be aware of too, is that when you're working with a problem, asking, are my vectors like 10-dimensional, in which case I'm probably fine doing some kind of Euclidean distance, or are they 10,000 dimensional, in which case Euclidean distance really doesn't make too much sense. So that's Euclidean distance, also known as L2 norm when we're talking about reference to the origin. And if there's a L2 norm, there's got to be an L1 norm. And that's what we'll talk about next, the L1 norm, or the Manhattan distance. Now again, take 2 points in space. The L2 norm, of course, is the straight line distance between them. But let's pretend now these 2 points in space are 2 points in a city, in Manhattan, for example. Now, the way to get from point A to point B, very roughly speaking, is that you can't just go from point A to point B straight line because you can't walk through walls and buildings. You basically need to take steps vertically, horizontally, vertically, horizontally, vertically, horizontally, until you reach your destination. And the total distance covered taking these vertical and horizontal steps, no matter how you exactly do it, the distance is going to add up to be the same. That distance is called the Manhattan distance, also known as the taxicab distance for the same reason. It's the path that a taxicab would take going through city blocks to get from point A to point B. Now again, if you talk about this, where the reference point is the origin, it's called the L1 norm. And so I'll flash that picture on the screen here. If we talk about all the points in space that have an L1 norm equal to 1, then you actually get a shape that looks like this diamond. So you can confirm for yourself, any of these blue points that make up the boundary of the diamond, you would need to take a path in terms of only vertical and horizontal moves, whose distance adds up to exactly 1 in order to get there from the origin. Now, the L1 norm's biggest pro is actually in the context of talking about lasso regression, which is an extension of ordinary least squares or just linear regression. I'll put our video on lasso regression in the description below. But basically, lasso regression is a way for you to extend linear regression so that the coefficients that you get at the end of the day are sparse, which means many of them are going to be exactly equal to 0, and only a few important coefficients are going to be non-zero. And this is a desirable property for many reasons in these problems, both because it regularizes your coefficients, keeps them from getting too big, so it solves this overfitting problem, and also as a form of feature selection, where if one of your coefficients got set to 0, you can rule that out as an important feature or a predictive feature in solving your problem. Only the ones that are not equal to 0 are the most important features in some sense. And the reason it does that is because when you use this L1 norm as a constraint, and if your x-axis is some coefficient 1 and your y-axis is a different coefficient 2, then these pointy parts of the diamond are going to be the preferred solutions. And any pointy part, one coefficient is equal to 0, so that enforces sparsity. That's a very hand-wavy explanation, but that's basically what's going on there. So the pro, of course, is very helpful with these L1 norm problems where you want to enforce sparsity in your coefficients. The con is that outside of that, this Manhattan distance doesn't have a lot of real-world applications. Of course, if you truly are trying to find the distance between one point and another in a small city, then this makes sense. But any other problem you can think of where the vectors don't represent actual physical points in space, it's a little bit harder to convince anyone that taking the L1 norm, taking the Manhattan distance here is a better idea than just taking the L2 norm. So definitely less useful and less intuitive in a general sense. Now let's stop and think for a second. We've talked about the L2 norm. We've talked about the L1 norm. What's stopping us from just putting whatever number we want in front of that L? Will that still be a norm that we can talk about? Well, the answer is yes. And that gets us into the Minkowski distance. So the Minkowski distance is interesting in the sense that it's actually an umbrella term which encompasses the L1 norm and the L2 norm as specific cases of it. So if we look at the L2 norm's formula, let's just say you have two vectors and you're trying to find the L2 norm. How are you going to do it? Well, you're going to go coordinate by coordinate, so that's represented by this big sum that's out here. For each of these coordinates, you're going to subtract the corresponding coordinate in the first vector from the corresponding coordinate in the second vector. You're going to square that difference, and then at the end, you're going to take a square root of the entire thing. Now, how do you take an L1 norm? Well, you don't square anything and drop the square. You'll have an absolute value instead on these xi minus yi, and you'll still have the sum, and you drop the square root. Instead, you have a 1th root, which is actually doing nothing, but we'll just keep it there because it'll be more clear what's going on. So this form for calculating the Manhattan distance looks remarkably similar for calculating the form of the Euclidean distance. It's just that we have 1s in the Manhattan side and 2 on the Euclidean side. No wonder they're called the L1 and L2 norms. So what if we just change that 1 or 2 to whatever we want? And that's exactly the spirit of how the Minkowski distance got constructed. If I put a 3 there, so now I'm taking the 3rd power of all of these differences, these absolute differences, and I take a 3rd root on the very outside, well, that's going to be a Minkowski norm with p is equal to 3. P is this parameter that controls exactly what instance of the Minkowski norm you're talking about. You put a 4 there, you got an L4 norm. You got a 5 there, you put an L5 norm. You can even do more interesting things where you put decimal things in there. For example, if the L1 norm gave us this kind of diamond shape, and the L2 norm gave us a circle, if I put anything between 1 and 2, I'm going to get a squircle. And this, besides being a fun word that was coined by Matt Parker, as far as I know, besides just being a fun word, actually has very interesting properties that is used and is in the spirit of something called elastic net regularization. So when you talk about lasso and ridge, you can actually do something between lasso and ridge, which often has the best of both worlds, which is called elastic net, where you take a little bit of the L1 norm and a little bit of the L2 norm, and that's called the elastic net regularization. This choosing a p in the Minkowski distance that is between 1 and 2 is a very similar spirit thing, where we're not exactly doing an L1 norm, we're not exactly doing an L2 norm, but we're doing something in between. We still get that curvature, but you still get the pointiness of the diamond. You can also go below 1. You can do a L0.5 norm, and now you get a diamond, but that diamond is like this. What is that? Concave or convex? Concave, I guess. Either way, the diamond looks like this instead. So of course, a lot of these are just pretty pictures and the use case doesn't always make too much sense. I would say the part of this domain where the use case is the most clear is when you're talking about things between the L1 and L2 norm because you're trying to get the best of both worlds. And the other place where this use case makes a lot of sense is sending this thing to infinity. If we send p to infinity, check out the shape that's being formed. It actually looks like a square now. And indeed, if you send p all the way to infinity, you get another special case of the Minkowski distance called the Chebyshev distance. So the Chebyshev distance is a very, very interesting one. It actually took me quite a while to wrap my head around what the use case of this would be, but there actually is a very, very convincing use case for the Chebyshev distance. So first of all of the points on this square here that you're seeing have a Chebyshev distance of 1 from the origin. So the L infinity norm, or the Chebyshev distance, from the origin to any of these points, these blue points you're seeing, is exactly 1. What does that mean though? If we look at one of these blue vectors, for example, let's look at 1, 0.5. What's the maximum value inside that vector? Well, it's 1. What if you look at 0.5, 1? What's the maximum value inside that vector? Well, it's equal to 1. What if you look at negative 0.5, negative 1? What's the maximum absolute value there? Well, it's equal to 1. Turns out, that is exactly what a Chebyshev distance of 1 means. No matter which of these blue vectors you look at that form the boundary of this square, the biggest absolute value you're going to find by just scanning through all the elements in this vector is exactly 1. It is the biggest thing in the vector, which you can argue is also a way to measure the size of a vector. What is the biggest absolute value contained in this vector? Where does that come helpful in a real use case? Well, if you just focus on the positive quadrant for this picture for a moment, and pretend the x and y axes represent the load on some software service that you're building. Let's say the x-axis is the load from one of your customers, and let's say the y-axis is the load from another one of your customers. And if I ask you the question of what is the minimum load that your system needs to be able to support, well, you would say I need to support the highest load of customer A and customer B. And it's exactly these maximum problems where you're saying the notion of distance for me is just the maximum of all of these different coordinates that I might be looking at. That's where Chebyshev distance shines. Because if we look at all of these vectors that make up this blue square here, then they represent all possible combinations of load put on our system by customer A and customer B, where the minimum amount of load we would need to support is equal to 1. For example, if customer A is putting 0.5 load on our system and customer B is putting a load of 1, we need to support a load of 1. If customer A is putting a load of 1 and customer B is putting a load of 0.25, we need to support a load of 1. It doesn't matter that there's a customer putting less load than 1. As long as there's at least one customer putting a load of 1 on our system, we need to support that. Admittedly, not something that comes up all the time, like Euclidean distance would, but when it comes up, that's exactly the distance you're going to go to. Now, last but not least, let's talk about cosine distance. The reason we didn't talk about cosine distance earlier is because the ones we talked about already fit a very neat narrative of L2 norm, L1 norm. What if you did something that's not 1 or 2? Let's send the thing to infinity, talk about Chebyshev distance. So that narrative is dealt with now. Cosine distance is probably the second most used distance measure in all of data science after Euclidean distance. And then after that probably comes L1 norm, the Manhattan distance. The big pro of cosine distance, first of all, what is cosine distance? Cosine distance is a distance measure between two vectors where you're talking about what is the angle between these two vectors.
Hey everyone, it's Ritvik from the edit. It's a good thing we've stopped on my silly face here because I also made a silly terminology mistake here. I'm going to start talking about the cosine distance, but I really mean the cosine similarity going forward here. So every time you hear me say cosine distance, please replace that with cosine similarity. The relationship between these two things is pretty straightforward. The cosine similarity is just 1 minus the cosine distance. Thanks. Back to you, Ritvik.
So in one extreme case, you have one vector that looks like this. You have another vector, it could be the same magnitude, could be shorter, it could be longer, but as long as it's facing in the same direction as that first vector, the cosine distance between two vectors that point in the exact same direction is going to be perfect, equal to 1. Now on the other hand, if you have one vector like this and another vector pointing in the opposite direction, again, doesn't matter what the magnitudes of these are as long as they're not equal to 0, then the cosine distance between those oppositely pointing vectors is absolute lowest, is -1. They're the most different you can get. And anything between that, so if you're almost close to each other, it's going to have pretty close to 1 cosine distance. If you're getting further, that's getting less than 1, less than 1, less than 1. Then once you cross over the 90 degree, in the 90 degree case, your cosine distance is 0, perpendicular to each other. Once you cross over that, it starts getting negative. All that is just to say that cosine distance purely just cares about the angle formed between two vectors. The smaller the angle, the more similar cosine distance thinks these two things are. The bigger the angle, the more different these two things are. And so that's actually the biggest pro and biggest con of cosine distance. Talking about the con first, as you might have seen in Euclidean distance, we care very much about these two things being close to each other. In cosine distance, it really doesn't care if they're close to each other, it just cares if their angles are close to each other. And so you need to be aware of that when consciously choosing cosine distance, because if the actual physical distance does matter, this is probably not a good choice, or you'll need to normalize it somehow so they're actually all on the same radius. But if the actual physical distance doesn't matter, if only the angle, or in other words, the ratio between the x and y axis or x, y, z axis as you get to higher dimensions, if only that ratio matters, this is the perfect distance metric. To give you a real world example, let's say you are talking about the wins and losses for a sports team, and each vector is made up of two elements, the number of games won by the sports team and then the number of games lost by the sports team. Let's say team A has 100 wins and 100 losses. Let's say team B has 200 wins and 200 losses. Well, these two teams are extremely similar. They both won half their games and they both lost half their games, and therefore the cosine distance is going to give them a perfect score of 1.0. And that is because we only cared about the ratio between items in our vector. We didn't care about the absolute magnitude in this case. Now let me give two honorable mentions. To be quite honest, I don't know if you're going to use these. I'm sure many of you will, but for the vast majority of you, probably these are not going to be on your radar at all, but they're cool. The first honorable mention is called the Haversine Distance. So if you have two vectors of the same size, the Haversine Distance is simply the number, if you go like first element, second element, third element, it's the number of these pairwise elements between the two vectors that are different from each other. So this comes up in information theory, but to give you a less serious example, Let's say that each vector represents whether someone ate toast or bagel on a given morning. And let's say that the first entry is for Monday, Tuesday, Wednesday, Thursday, and so on and so on. You can measure how similar two people are by how many instances there are where they both had toast or both had bagel, and how different they are by whether one of them had one but the other had the other. So that's one use case of Hamming distance. Another interesting one is called the Haversine distance, which measures the distance between point A and point B, but on a sphere or on a globe. So this has a very obvious use case when you're working with actual geospatial data, and the straight line distance doesn't make sense because it's going to go through your planet, and that's not a valid path. This is telling you what's the distance between point A and point B on a sphere. If you have an ellipsoid, you can do an extension of this called the Vincenti distance. So again, pro, obvious use case, con, obvious use case. So that's about it all. I would say the key takeaway is that Euclidean distance, the cosine distance, and the Manhattan distance make up 99, maybe 0.999% of all use cases you're going to deal with. And so it's very important to have a functional understanding of the pros and cons of those. But that doesn't mean you can ignore all the others. There are very obvious use cases for all these other distances we talked about. And if nothing else, it just helps to be aware of them to make you a better data scientist. Any questions at all, please leave them in the comments below. Thank you so much. Look out for that video on 100,000 subscribers, and see you next time.